Welcome back to this video series on acid-base equilibria. So we're going to pick up with the relative strengths of acids and bases. Okay, we have briefly mentioned the acid ionization constant. When we are talking about the relative strengths of acids or bases, we are talking about the extent to which that they ionize when dissolved in water. So strong acids and strong bases will ionize essentially completely. For the purposes of this class, we'll consider the ionization to be complete. And then for weak acids and weak bases, they will only partially ionize. And so we have this general reaction for weak acids, and we'll see and use this reaction quite a bit. So you may want to take note of it. The HA, of course, represents the weak acid. Okay, and this is of course just a generalized equation, so that could represent any weak acid. And then reacting it with water, so it dissolves in water to form your hydronium ion, which we've seen before, and then A negative represents the conjugate weak base. Okay, and so if we establish an equilibrium constant for this reaction, we get the acid ionization constant, which we represent as Ka. And if you notice, water is not included in this, again, because water is a liquid, and so we ignore anything that is in the phase of a liquid. And that gives us our products, which are the hydronium ion concentration and the conjugate base concentration divided by the weak acid concentration. Now, the larger the Ka value, the stronger the acid, because we said that strong acids will completely ionize. And so the more ions that you have, the stronger that acid is. And so you notice that both of your ions are in the numerator, right, of the fraction. And so the larger your Ka value, the larger amount you have of ions. And then if we want to look at the percent ionization to see exactly how much that something ionizes, we'll compare the hydronium ion concentration at equilibrium. So remember the EQ stands for equilibrium, and divide that by the original concentration of the weak acid. And so remember that 0 stands for the original, or we'll use the word initial for your ICE table. Okay, and then of course times 100, so we get it in terms of a percentage. Now we have what's called the 5% rule. This is going to be very important when we look at equilibrium calculations. If that percent ionization is less than 5%, then we can assume that the original concentration of the weak acid and the equilibrium concentration of that weak acid are about the same. And if we do that, that will avoid using the quadratic equation when we're looking at our calculations. So this 5% rule, we'll keep using it when we look at calculations, but just remember less than 5%, then we can assume that the equilibrium and initial concentrations of the weak acid are the same. Okay, very quickly, base ionization is going to be very similar. We've got the general reaction here of B, which represents our weak base, of course. And dissolve that in water. And then on the other side, we get the conjugate weak acid. Plus our hydroxide ion. And so again, if we look at the base ionization constant, we ignore the water because it's a liquid, and then that leaves our two ions, the conjugate acid times the hydroxide ion concentration divided by that weak base. And so again, the larger the Kb value, the stronger the base, because the more ionization that you have to have. And if we look at the percent ionization there, we're going to take the concentration of the hydroxide ions at equilibrium divided by the initial concentration of the base times 100%. Now we do have two general reactions for base ionization constants. You can use this one, and that's probably the one I will use throughout the videos. But there is a second general reaction for weak bases. And the second type of reaction that we have here, all they're doing is taking the general reaction for the acid, that's the first one listed, and swapping it, right? So this, again, A negative would be your weak base. And then HA would be the conjugate acid to that. Okay, so you can write the weak base general reaction in two different ways depending on what your weak base looks like. If the weak base has a negative charge, then it's helpful to use this reaction. If your weak base does not have a negative charge, then it might be easier to use this first example. Okay, but given these two reactions, we can look at how the Ka and the Kb values relate for a weak acid and its conjugate base pair. And so that's why we've used this second example of the weak base reaction so that we can get things to cancel out. So if we take the weak acid reaction and the weak base reaction and add those two reactions together, and assuming that the arrows represent equal signs, so right, anything that is on the left and the right hand side of that equal sign we can cancel out if they're identical. And so we see that we've got this HA that is on the reactant side of the first reaction, and then HA that is on the product side of the second reaction. And so because those are on opposite sides, they will cancel out. Okay, and if you went back to some of your Hess's law examples from maybe General Chemistry 1, same concept here. And then we also have that weak base, that A negative. It's shown on the product side in the first reaction as well as the reactant side in the second reaction. And so those will also cancel. Okay, and so what we're left with is that we have two water molecules, two H2O, leaving out the phases for a moment, will give you the hydronium ion plus the hydroxide ion. Okay, and so we'll remember that that is the reaction that we use to form our original Kw value for water. And remember that Kw was equal to 1 times 10 to the negative 14th. That is a constant for the autoionization of water. So we know what Kw is equal to, and we know what Ka and Kb are equal to, right? So Ka represented here is the hydronium ion concentration times A negative divided by your weak acid. That is your Ka value, and then multiply it by your Kb value. Okay, when we add two reactions together, we can multiply those two equilibrium constants, and you will see that the A negatives will cancel and the HAs will cancel just like they did in the general reaction. And so you get back, the only things that are left are the hydronium ion concentration and the hydroxide ion concentration. And so you realize that is the same equation as it is for Kw. Okay, and so you get this overall expression that Kw is equal to the multiplication of your acid and your base ionization constants. And so because they are inversely related, just like pressure and volume in our gas laws, if one goes up, the other must go down. And so the stronger the acid, the weaker its conjugate base will be. Or the stronger the base, the weaker its conjugate acid will be. Okay, so let's look at one quick example. What is the ionization constant? So we're talking about that Ka value for the weak acid and the conjugate acid of the weak base where they give us the Kb value. Okay, so they're asking what is Ka? What is the ionization constant for CH3NH3 positive, which is a methylamine. So we know that Kw is equal to Ka times Kb. And of course we can rearrange this equation where Ka will be equal to Kw divided by Kb. Okay, and the Kw is known at 25 degrees Celsius to be 1 times 10 to the negative 14th. And then divided by the Kb that they give you, 4.4 times 10 to the negative 4th. Okay, 2 sig figs, especially for the Kb number. Kw, we could get 3 if we needed it. And so we get back Ka equals 2.3 times 10 to the negative 11th. Okay, so simple enough. But we will use this because a lot of times when we are looking at equilibrium calculations, they may only give us the Ka value for the conjugate acid, and if we are looking at the weak base, we'll have to use this to calculate what the Kb value is. Okay, so typically Ka values are given, and if we need to do a calculation with a weak base, we have to usually use this equation to figure out what the Kb is. Okay, so in most textbooks, you'll see a spectrum of your increasing acid strength or your increasing base strength. So acids will typically be listed on the left and bases on the right. And so if you look on the left with the acids, you'll see this water line. Okay, if you are below that line, you are considered to not be a Bronsted-Lowry acid. So this doesn't mean that they can't act as weak acids. It just means that when it's in connection to water, it will not ionize, right? So it will not donate a hydrogen or a hydrogen ion to water to form that hydronium ion. Okay, so anything below the water line is considered to not be an acid in water. And then above that line, as long as you are below the hydronium ion, okay, this section is going to be your weak acids. And then if you're above that hydronium ion line, you are considered to completely ionize into hydronium ions in water, and so those are going to be your strong acids. Okay, and then same thing on the base side. You can find that line for the water, but it's going to be opposite. So this time, if you are above the line, you will not ionize in water. Okay, so again, you will not take a hydrogen from water in order to form that hydroxide ion. So those do not ionize and are not considered bases in the Bronsted-Lowry definition. And then below the water line, as long as you are above the hydroxide ion, those are going to be your weak bases. And below the hydroxide ion, those will consider to be your strong bases. Okay, so if we're not given a list or a spectrum of the acidity, or you're not given those Ka or those Kb values to determine the strength of your acid, there are a few trends to the periodic table. So as you go down a column, what happens is that the size of your atom increases. And of course, it's going to be attached to the hydrogen. And so we look at any other atom, we'll label it as A. And let's say the size of A in the beginning is here. And then as you go down the periodic table, the size of A is going to get much larger. And so you have a farther distance from that hydrogen atom, and so you get a weaker bond. And the weaker that your bond is between the atom and your hydrogen, the stronger the acid is going to be, because the more likely that that hydrogen will be donated. And it's easily donated because the bond between the hydrogen and the atom it's attached to is considered to be weak, right? So the weaker that bond is, the easier it is for that hydrogen to pop off, and therefore the stronger the acid. And so you'll see, especially with your halogens right here, that hydrofluoric acid is going to be considered a weak acid, but everything below that, hydrochloric, hydrobromic, and hydroiodic, those are going to be your strong acids. Now, if we're looking across a row, then it's going to depend on the electronegativity of that atom, right? So electronegativity, we know, increases as we go across the periodic table, where your most electronegative element is fluorine, followed by oxygen, and then nitrogen. And so the more electronegative that an atom is, the more likely that it's going to hold on to those electrons, and it will be easy for that hydrogen to pop off. And so again, you're going to have increasing acid strength. And so overall, your increasing acid strength is going to go down and to the right, so that hydrochloric is your strongest. Okay, and then another effect that we see with molecular structure is based on the number of oxygens that are attached to the central atom. And so this is talking about those polyatomic ions that have a hydrogen attached to them, like nitric acid, nitrous acid. You've also got phosphoric and sulfuric acid. So when you increase the number of oxygens on that central atom, you are increasing the oxidation number of the central atom and essentially making it more electropositive. And so what happens is that in this case we have nitrogen with a 3+ versus nitrogen with a 5+ charge. So the larger that positive charge is, the more that it's going to attract the electrons that are on the oxygen next to it, right? So it's going to pull all those electrons closer towards that nitrogen. And when that happens, again, it makes it easier for that hydrogen to pop off, because we get a weak bond between the hydrogen and the oxygen, because you have a stronger bond between the oxygen and the nitrogen. So the weaker that oxygen-hydrogen bond is, the easier it is to pop that hydrogen off and donate it. Okay, so again, just keep in mind that as you increase the number of oxygens on that central atom, you will increase the acidity, because it is easier to donate that hydrogen. Okay, so we will end this video here, and then in the next video series, we will pick up with calculations on acid-base equilibria.